Hello, everyone. I'm very happy to have the opportunity to represent my paper here. The title is Improved Linear Hall Attack on Round-Reduced Statement with Dynamic Key-Guessing Techniques. This is a joint work with Xiaoyun Wang. And for the first part of the report, I will introduce the background and the contributions in brief. Summon is a family of block ciphers proposed by the National Security Agency in 2013. There are 10 versions of Summon with different block and key size. It's a 5-store structure with very simple round function, and the round function consists of bitwise AND operation and rotation operation and bitwise XOR operation. They are designed for optimal performance in hardware applications. Since its proposition, many cryptanalysis results come out. For example, Academy et al. Proposed the first differential attacks on Siemens, and then FSE 2014. Abed et al. And Boykov et al. They independently searched some differentials for Siemens and improved the attacks. Then later, Wang et al. They improved the attack procedure for linear and linear Hall attacks. There are also many results. Abel et al. They gave some good linear trios for Siemens, and later Alizada et al. Improved the linear attacks. By using the connection between the differential characteristic and the linear trio, Abadari et al. They transformed many differentials into linear halves directly. Later, Shi et al. And Sun et al. They searched some new linear halves using the mixed integer linear programming technique. Also, there are many other attacks, for example, the impossible differential attacks, the zero correlation attacks, and the integral attacks, here. Then, for these existing cryptanalysis results on Siemens, there are mainly two directions. One is to search bad distinguishers. For example, the differential distinguishers and the linear distinguishers. Maybe some are, for example, some differentials found and FSE 2014. Also, for some linear house distinguishers, For some linear house distinguishers, some are got for using the connection between the differential and the linear characteristics. Another direction is to improve the attack procedure. One work is done by Wang et al. They improved the differential attack using dynamic key-guessing techniques. So we thought whether the dynamic key-guessing techniques can be applied into linear attack. So we do this work in this paper. And in this paper, we propose the dynamic key-guessing technique for linear attack. It mainly consists of 3 parts: guess, split, and combine. It means at first we get some key bits, and then split the plain text or cipher text into different sets. And in each set, we compute the partial correlation. And at last, we combine them together according to the key value. Using the dynamic key-guessing technique, we improve the linear Hall attack on all versions of Simon. For example, we can attack 23 rounds Simon 32 with key size 64. Also, we implement the 21 round attack on Simon 32. Then in the second part, we introduced the techniques we used in the linear cryptanalysis to reduce the time complexity. And first, we begin with the general framework of Matsui's algorithm 2. Usually given a linear Hall with input mask alpha and output mask beta, one usually add some rounds before and some rounds after the linear Hall to attack more rounds. Suppose y is the target parity bit we want to know the bias. It can be written as a function of plain text, ciphertext, and the subcase involved. So we should compute this formula. And the time is computed as this. Later, Matsui improved this procedure and first compressed the plain text and ciphertext. It means only the involved bits are considered. Also, the key is compressed at first. So now the target bit y is a function of x and k. So now we need to compute this formula in the attack. And the time becomes 2 to L sub 1 plus L sub 2. Usually this is smaller than the original one. In a further step, if y is linear with some bits of x and k, for example, y is linear with x sub 0 and k sub 0, this bit can be compressed at first, like this. Just now the k bit k0 only affect the signs of big ky, so we do not need to get it in attack. And now the time becomes this, and it's smaller. Here we denote the k sub 0 as a related bit. If there are multiple linear bits, we also do the same procedure as above. We just compute the XOR sum at first, and then it becomes this situation. Then I will introduce the dynamic key guessing technique in the linear attacks. For a Boolean function y equal to f x key and a count vector v, here we denote the number of x. So in a straightforward method, computing this needs about 2 to L1 plus L2 calculations. But if for different keys the expression of y is different, the key can be guessed dynamically, like this. For example, if let k be the concatenation of these 4 parts, and if when kj is known according to the value of x and kj, maybe the x can be split into 2 sets, set A and set B. In set A, the target value y is independent of k sub B, and in set B, y is independent of k sub A. So if this case exists, we do not need to guess all the k values. So the attack procedure becomes this. get kg and first, and then split the x into two sets at this, and we compute the partial correlation in each set. Compute this and this. Then, according to the value of key, we combine them together. So now the time becomes this. Here, this is the size of a key sub g. So usually this complexity is smaller than the original one. So this is the main idea of dynamic key guessing technique. Here is a simple example. Y is a function of x and k. These are 2 bits. This is and first we guess k sub 0. If for the x with x sub 0 equal to k sub 0, we know the left part here is 0. So we do not need to guess the k sub 1 here. And we can just add the 2 counters and get a new counter t sub 0. For the x, then x sub 0 not equal to k sub 0. Here, y is a function of this. So here, we can say y is linear with this. So using the linear compression technique, we just get a new count t sub 1. Then, according to the value of key, there are according to the value of key, we combine the 2 counters to get the correlation. So here, the new complexity becomes 2 to 3, while the original one is 2 to 4. In the third section, we introduce the improved linear Hall attack on Simon. Here, the parameters of Simon of all the 10 versions are listed in this table. This is the run function of Simon. It's very simple. From this figure, we can see that any bit in the left part of the output is a function of 4 input bits and 1 bit of subkeys. The right part is just the same as the left input. Here, this table shows all the linear halves found now. The black one are the linear halves we used in the attack. Notice the first 13 round linear halves for 732. They are in fact the same in the rotational sense. The rotational property says that if there exists a linear Hall for 7 like this, after some rotation, the potential is same with the original one. So, but here, the 2 potential is estimated differently. So we chose some case and compute the empirical bias, and the results are shown in this table. From this table, we can see that about here, about 26% case are with potential larger than this. This table will help us estimate the attacker complexity and success probability more accurately. So we used this linear Hall with the input mask, with the input active bit xi, L5, and the output active bit this. if we using the run function of Zeman, we get this. It can be written as a function of this. So we let x sub 0 be this and k sub 0 be this. We get xil5 is this. Like this, we expand it for once backwards. We can get a function like this. It is a little complicated, but all the each bit of the x can be computed from the xi minus 4. It is shown in this table. We can compute this from the, if we just add 4 rounds before xil5, we can get this from the plain text. Also, for the output active bit, the expression is same with this function. Notice in this table there are 2 linear relations. So in the attack, so there are only 15 independent bits for x, and there are 17 k bits of key. Using the linear compression, we can compress x sub 0 and first. Now only 14 independent bits of x remain, and 16 bits of k remain. Now k sub 0 becomes the related bit. So here we begin use the dynamic key guessing technique. And first we guess k sub 1, k3, k7 in this formula. After we guess these 3 k bits, and then according to the value of x1, x3, and x7, we can compress some bits. For example, if this is 0, we can compress x sub 2 directly. Others are similar. So for case 0, 0, 0, the new expression is like this. There are only 8 independent bits remains. And to get, and also 3 bits are compressed to get this. And so we're getting the to store the new counters for these x values. We need t sub s additions. This is guess and split it into 8 cases. And for the other 7 cases, they are similar with case 0, 0, 0. So then we need to compute the correlations in each case. It is like this. Also, here to compute the correlation of f00, we also use the guess, split, and combine technique. Just receive this technique, and we get the total time is about 2 to 11.19 additions. So in total, the time of computing correlation of f is about this 2 to 19.46. And if we add 4 rounds before the distinguisher and 4 rounds after the distinguisher, and set the date complexity as this and advantage as 8, the time is the attack complexity is like this. It consists of 2 parts. One is to compute the bias for all the key guessed, it is like this. And also, after get the right key candidates, we execute the others. It needs about 2 to 56 encryptions. Since this complexity is small, we can add some other rounds to attack more rounds. It is like this. We can attack 23 rounds, 732. Also, we implement the 21 round attack on 732. According to the distribution of the empirical potentials, we can calculate the expected success probability is here in this range. In our experiments, the experimental success probability is about 28%, which coincide with the expected success probability. Also, for the time, it takes about 11 minutes for the data collection part, and it takes about 11 minutes to decrease the key space by 8 bits. The source code can be is shown in the print version of this paper. Here is the summary of the linear Hall attacks on Simon. We can see that our attack can attack more rounds. Thanks for your attention.